And you're not even trusting the bad apple in the group. You're actually trusting potentially somebody outside the group who can either coerce or hack either the bad apple or the most incompetent of the certificate authorities, whoever. So you're actually trusting way, way more than 1,000 entities whenever you connect to any HTTPS website.
So every single one is a single point of failure.
Yeah, every single one is a central point of failure for the entire internet. Why? Because every single one of these certificate authorities has the power to create, to sign certificates on behalf of websites. And it's a great business because it costs them $0 to do this, and you pay them a yearly fee for most of them. There's about 2 certificate authorities, to my knowledge, maybe 2.5, 3, something along those lines, that actually will give you a certificate that web browsers respect for free. One of them is called Start SSL. The other one is a project that I think is a collaboration between the EFF and Mozilla, which just started recently, called Let's Encrypt. And the reason why I'm telling you that is because don't be a fool. Don't pay for insecurity. The companies out there who are paying for hundreds of dollars a year for these fancy green bar, there are some certificates called extended evaluation certificates or validation. They cost more than other kinds of certificates because they make the color of the address bar change.
What's the web? Who gives you the free one? Can I
Start SSL. It's one word. Start SSL. So one is Start SSL. They're a little bit more difficult to use than Let's Encrypt. But you can use
wildcard?
They don't do wildcard. What they do is they give you one domain and one subdomain. And usually the subdomain is because most people have www as a subdomain. And Let's Encrypt, I don't remember what the deal with them is. But it's effectively a wildcard because you can just keep asking for they don't have a limit, really. I think they do. Like they might have like a script. If you start like getting a whole bunch of them, they might stop. But other than that, you can ask pretty much for as many as you want, as long as you're being reasonable by their terms. So companies that pay, companies like PayPal, all the banks out there are paying, and other websites pay hundreds of dollars for these fancy certificates that make the address bar green. They're wasting their money because most consumers, most web users are not going to notice whether or not when they go to a website the address bar is green or not. That's not even something that they even really understand is a meaningful thing. They just want to know if when they go to paypal.com if they're able to see it without any kind of warnings. That's number one. Then for probably a small fraction of those people, they care if there's like a little lock icon, if they can see that lock icon. And then for a tiny, tiny, tiny fraction of those, they even know that the thing is supposed to be green, a different color or something like that. So anybody can, or not anybody, but a lot of, somebody can obtain a fraudulent certificate from one of these authorities, either by hacking them, by coercing them, etc., and then use that to man-in-the-middle financial websites or anything else. And most people are not going to notice that happening. It's very, very difficult to detect these attacks. And yes, they do happen. Question?
So all of these CAs are supposed to have a key in the browser, right? So browsers only have so many, if you look at it, they've got like a bunch of keys in there that are from CAs they trust, I think.
Yes.
Is that correct?
Yes.
So if you have like whatever Start SSL just wants to be created by the EFF, how are they going to get their keys into browsers?
Okay. So the question is, comment then a question. Comment is, so web browsers ship with a list of certificate authorities, the public keys to them that they trust. So if you want to create a new certificate authority, how do you get your certificate authority's public key into one of these lists? There's probably a process for doing that in place. I'm fairly certain there is a process in place for doing that. And the answer is that it's not easy to get your certificate authority's key into a web browser. And that's one of the reasons why there are so few certificate authorities that are trusted by web browsers that offer free certificates. EFF was able to get this Let's Encrypt thing going because they had a collaboration with Mozilla, and Mozilla happens to have their own web browser, and Mozilla collaborates with Google, who also has their own web browser, etc. Yes, back there.
So actually the situation is sort of much worse than you're describing. It's almost routinely people are being man in the middle because a lot of businesses, want DDoS protection. So they often will, work with either a CDN.
Are you talking about Cloudflare?
Yeah, or yes, I mean, any a CDN or any DDoS protector will actually be a man in the middle. That's the only way they can do the job.
Yeah.
And so people are being routinely man in the middle in the name of like.
In the name of security, man in the middle in the name of security.
That's also how like all the firewalls and APs that do traffic filtering are doing it now too.
I didn't quite catch how this.
Okay, all right. So I'll comment. So the comment was that he said that the problem was actually worse than I'm describing it, which it's hard to imagine how it can be worse. But yes, he's right. It's worse than I'm describing it because it's now become very fashionable because these things are because getting a free certificate is not easy. There are companies like Cloudflare who provide DDoS protection, distributed denial of service, against websites. So they provide protection from that attack. And lately they've been offering free HTTPS to their customers. And how are they doing that? They're not doing it the way that Start SSL and Let's Encrypt are doing it. They don't have a certificate authority in web browsers that's accepted by that's accepted by web browsers. What they do is they use a technical thing called subject alt name to they buy their own certificates essentially, and they tack other people's websites onto these certificates. And because their certificates are legitimate, when they add other domain names to that list of certificate, those kind of gain the legitimacy that they're already, they kind of grandfather them into their certificate, is what they do. And it is a man-in-the-middle attack that people either knowingly choose to participate in or unknowingly choose to participate in. I suspect that for most people, for most businesses that go with Cloudflare, it's mostly unknowing. Like they think they're securing their visitors' connections, but what they're doing actually in reality is Cloudflare is becoming this huge central point of potential failure and also potential point of surveillance, where, especially, and it becomes, the more customers that Cloudflare gets, the more of an incentive there is for a government to come to Cloudflare and say, listen guys, you know that little step you do where you decrypt and re-encrypt traffic? Just please add a little copy of all of that information and send it over to us. And don't tell anyone else you're doing that because we just sent you a national security letter. And then people think that they are, again, they have that little lock icon and they think they're being secured, but in reality, that's not at all what's happening.
Yeah, it's not to make Cloudflare out to be a bad guy, because what I'm saying is that, before them, you had CDNs, and some of the CDNs tried to offer you SSL with the CDN. The only way they do that is by doing what we described Cloudflare is doing.
Right. So yeah, Cloudflare isn't the only one.
And similarly for people who were saying they were providing DDoS protection with SSL, this is what they needed to do.
Yeah, so CDNs, content delivery networks, often use the same trick, or technique, not trick. Content delivery networks, they specialize in making copies of your content and putting them on servers around the world so that your content gets to people really quickly. And so they have to, because they have to decrypt and re-encrypt traffic, otherwise people won't be able to understand the garbled mess for your JavaScript or your CSS, etc. So these kinds of attacks are happening routinely, sort of knowingly and unknowingly, just because of how encryption works. And then they're also happening as legitimate attacks. And the problem with this is that it's incredibly difficult to detect one of these attacks. To give you an idea of just how difficult it is to detect one of these attacks, there are only a handful of companies on the entire planet that are, first of all, capable of detecting one of these attacks. Really, because and those are the companies that make web browsers. Because they're in this special privileged position where they can modify their web browser however they want. And so, for example, one of the most notorious attacks, like probably the most notorious attack to date that happened was the DigiCert attack of, I don't remember, it might have been 2008 or something like that. And the reason that attack was detected was because Google is aware of these attacks. So what they do is they say, for our websites, for Google, we're going to take our certificate authority, we have our own, and we're going to pin, that means we're going to take our public key and we're just going to put it into every copy of Google Chrome that we distribute. And since the web browser now knows what the public key should be, they can detect if the public key is switched on them. But notice a few things. This is Google protecting their own websites. They cannot use this technique to protect other people's websites. This is Google. So that's one of a handful of companies. The other companies that can use this technique are Apple, because they have Safari, Microsoft, because they have Internet Explorer, Mozilla, because they have Firefox, and for the small fraction of people who use Opera, there's also Opera. And that's it. And in spite of that, it took Google about 2 months before they detected an attack that was happening on their users as they were connecting to Gmail from, like, I think it was Iran or something like that. So 2 months. In spite of being one of the few organizations that's capable of detecting these attacks, it took 2 months to actually detect it. And when they detected it, they discovered that this attack was being done actually not just on Gmail and not just on Google websites, but on U.S. federal government websites, like the CIA.gov, FBI.gov, and I think hundreds or thousands of other websites. And it was a huge scandal and all that. But these attacks probably happen routinely, and they're incredibly difficult to detect because the system calls the attacks legitimate. As long as you have a certificate that's been signed by one of these certificate authorities, the system doesn't actually view it as an attack. It considers it to be a legitimate secure connection. And when you have a system that cannot differentiate between legitimate secure connections and man-in-the-middle attacks, you have a big problem. Yeah. So,
I'm sorry to jump ahead a little bit, just so that I get the picture here. I think what you're going to suggest is that you can use essentially the public keys on a blockchain to replace the CAs. I'm sorry I'm jumping ahead, but I'm just trying to get a picture of how this is tying in. Is that correct?
That is correct, but my plan is actually to annoy you guys with problems before I get to the blockchain.
Okay, okay, so I'm just trying to see how it's fitting in. Thank you.
Okay, so moving on to the next problem. So this is HTTPS. This is the mess that we find ourselves in with HTTPS, with these certificate authorities. The basic idea is that we're trusting people who should not be trusted. That's a bad idea, and that's why we have this problem. What's another problem that we have related to public key infrastructure? Another problem that we have is GPG. Why is GPG a problem? GPG is a problem because it's one of the few methods right now that people have for sending secure email to each other, or secure messages to each other. But it's for the technical elite only. Regular users need not apply. And in spite of lots of great projects out there trying to make this stuff easier, you cannot make GPG usable if the user ever hears the word public key. So it's just not going to happen. So when GPG becomes usable is when users never have to worry about public keys. How does GPG work? GPG has, again, a similar problem, which is how do you get somebody's public key to send them an encrypted message? Currently, there are what are called GPG key servers out there, and you search the key servers for an email address, and they're supposed to return to you the public key for that person. There's multiple problems with this. First off, oftentimes, when you search for an email address, you get multiple results. So how do you know which one of those public keys is the right one? Another problem is that the connection to, oftentimes, might not always be the case, the connection to these GPG key servers is sometimes just in HTTP. So a man-in-the-middle attack can be done to swap out the keys as you're requesting them. Sometimes it might be over HTTPS, but then you still got this other man-in-the-middle attack I just described happening. Then there's another problem, which is, well, and this happens all the time, by the way, like happens to me and my friends. Your computer dies, you lose your private key, and you have to generate a new one. So now, any secure messages that you get, first of all, you cannot read anymore. And second of all, you have the problem of convincing people. Sometimes you can't even meet them face to face. Sometimes you're communicating with people on the other side of the world. So now you have to convince them, oh, no, that's not my public key anymore. Use this one. Now that you're putting the other person in the position of figuring out whether or not you're lying to them and trying to attack them by telling them, some sort of a fake public key. And not just that, but then they have to actually go through the rigmarole of getting your new public key and updating their software with the new public key so that they can now send you encrypted messages again using the new one. So GPG is a usability nightmare because of that, and it will never become, there will never be a GPG for the masses as long as users have to deal with these private keys. Oh, there's one other problem I forgot. There's this concept of revocation also. And the concept of revocation exists both as a problem in HTTPS and GPG. Revocation is what you're supposed to do. It's a thing that nobody does, but you're supposed to do when your private key is compromised, or you lose it or something like that. So when you lose a private key, or your private key is compromised, you're supposed to make a statement in these systems that says, my private key was compromised, or whatever. Don't use that public key anymore out there, it's illegitimate. And you're supposed to send this statement over to some entity, some authority, that then is supposed to tell other people about it. Nobody does this. Nobody does this. By nobody, I mean like for really small values of, small values of 1. Because sometimes in GPG you have to create these like revocation things in advance. And if you haven't created a revocation thing in advance before you lost the thing, you can't create it in the first place. And then it's just confusing how to do this. Most system administrators don't realize this. They just update the public key and the private key that they have and use that. And that's a nightmare, by the way. That is a really insidious attack. That's the worst man-in-the-middle attack that can happen to you. And I think it happened to me. I'll describe how this works. So if you remember, a while ago, there was this huge kerfuffle called Heartbleed. What was Heartbleed? Heartbleed was just a software bug in OpenSSL. OpenSSL is like the software that secures the entire internet. It's what powers TLS. And TLS, by the way, for those who don't know, is the underlying protocol that adds the S to HTTPS. So I was connecting to NPM, Node Package Manager. And I have this web browser extension installed that you guys might want to install, but I really can't recommend it too much because it's a nightmare in terms of usability, and it illustrates again other problems with the system. Certificate Patrol is a Firefox-only browser extension that will tell you anytime a certificate changes. It will give you all the information about what changed, and it will tell you whether you want to accept or deny. So I was using NPM. And then one day I noticed that the certificate changed. I don't always do this, but whenever I see that, sometimes I reach out to the people who run the website. And I ask them, is the fingerprint that I'm seeing legitimate? So I did this on Twitter, and this was after Heartbleed. And this was because everybody at that point in time was changing their certificates because of Heartbleed. It was a nightmare for me to browse the internet because every website I visited, I'd get this thing. Firefox would slow down. I'd get this giant sheet that would tell me that the certificate changed. So I reached out to Node Package Manager, to NPM, and asked them, did this change? Is this your correct public key fingerprint? And they said, yeah, that's the correct one. And for probably 99.999 repeating % of the people on the planet, you know, that would have been the end of the story. But I thought about it a little bit and I asked, okay, wait a second, when did you make this change? And they were like, oh, about 2 weeks ago. And then some alarm bells went off in my head. Because I had been visiting NPM, the Node Package Manager website, fairly regularly during this time. And I'm pretty sure I visited it just yesterday, the day before that happened. And I'm pretty sure, well, yesterday I didn't see any kind of certificate change. So if they changed the certificate 2 weeks ago, why was I only just now seeing the change, in other words? So that's an example of what could have been potentially a man-in-the-middle attack on me or other people. Because of Heartbleed, you could extract the private key from any website that had HTTPS. That allowed you to man-in-the-middle connections, and it allowed you to man-in-the-middle connections using a legitimate certificate. One that the website actually created. Not one that was obtained from some other certificate authority, but the actual legitimate one. And then there's this, you know, so there's this man in the middle that's in the way, and you're seeing the legitimate certificate that was obtained thanks to a bug. And only until the man in the middle leaves will you actually see the legitimate one. So that's a particularly insidious form of a man-in-the-middle attack. And again, these kinds of things just are not detected. They're very difficult.
So are you sure that that's what happened, or is there some other explanation?
So yeah, we had a back and forth on Twitter to see if there was some other explanation. Some theory was that, well, maybe the old key was cached or something like that. But I doubt that it was cached for 2 weeks. I don't think that it's supposed to be, you know, cached for that long of a period of time on a CDN when it's changed. And I also don't understand how it even could be cached, because if they change the public key that they're using, I mean, the CDNs would need to, yeah, so it's, yeah. I don't know, but it's dangerous. It's dangerous for multiple reasons, and especially dangerous in the example that I just gave, because what is NPM? Node Package Manager is a centralized repository of software that all of you guys are using, most of you people are using, to install software on your computer. And then, so you're getting software from the central repo that could be man in the middle to install backdoors on software. You're putting that in your projects, and then you're distributing your software to other people. So you could even have a security audit on your code, and they could say, yeah, everything's totally legitimate. But you make a release all of a sudden, you know, the NSA or somebody just like swaps out the code, you know, in real time, adds a little thing into there, a go-to fail or something like that, one extra one, and boom, that's it. Suddenly, a project that's being used by hundreds of millions of people has a backdoor in it. Huge problem. I told you I would annoy you with problems, so I'm going to annoy you with another one. Here's another problem. This one comes from the area of privacy. So far we've been talking about security. Now I'm going to move into the realm of privacy, and I told you that would be a theme of this talk. The difference between privacy and security is privacy is when I care whether or not people know what I'm doing, and security is when I care about the integrity of data, and that it's not knowable. So security, you can have a secure connection to a website,